Now, good morning. So, welcome to the White Academy. So, this morning we'll be looking at organic sentences. Um, Nature has designed in such way that almost essential, molecules, there is a way actually they are synthesized, biochemically in nature. All right. So, when we talk about organic synthesis, actually, as chemists, we go into the nature, we study what is happening there, and then we come into the laboratory and see how actually we can make a prototype of such a thing. Is that okay? So we call that chemical synthesis, okay? But then, having studied what is the biosynthetic pathway, of those molecules. So this morning, we'll be looking at biosynthetic pathway for the synthesis of um, from 2,3, oxido squalene, okay? How we can obtain beta amyrin and several other products. Is that okay? So there are intermediates in between, which actually we will see as we go on, right? So first of all, let's look at squalene, the structure. Now, squalene actually is a kind of regular terpenoid. Is that okay? It's a C30 molecule, all right? So now, let's say from organic, synthesis, or let me just say chemical point of view, how do we go about such a thing? Now, these are the structure look like. So this how squalene structure. So this how it looks like. Okay. So like I told you, it's a form of it's a form of terpene. All right. So it looks like this, almost having a kind of, so to say, six, ring one, two, three, four, five, having six, multiple bonds, double bonds, one, two, three, four, five. So now, the most important thing now is actually how do we go from here? I talk about two, three, oxidosqualene. All right, so from this, actually, we want to enter and find out, okay, how do we generate beta amyrin, you know, alpha amyrin, and several other intermediates, okay, in between. Are we there together? So now looking at this from chemical synthesis, the very first thing to do, okay, let me number it so that actually you can get it so very well. So we have one, we have two, we have three, four, five, six. We can number and so on like that. So those are called carbon atoms. Carbon atom one, carbon atom two, three, and so on. So now, from the basic knowledge of alkenes, when you have alkene, all right, you can do a kind of simple oxidation, all right, usually making use of O2, with silver at about 250 degrees centigrade. Is that okay? So when you do such a thing, actually, what you end up is a peroxide. This is what you end up at the end of the day. Is that okay? Another thing again you can do is a kind of halogenation in the presence of water, that is an aqueous solvent. All right. So for instance, now if you brominate, is that okay? In the presence of H2O. So what you obtain is an haloadrine. All right, which actually consists of a bromo atom and then an hydroxyl group. Is that okay? So in the course of this, actually, we can eliminate either of these two so that actually we go from here and then we also obtain a peroxide. So, but then now, most importantly now, so if that is the case and then this is a squalene structure which actually undergoes such a thing, a 2,3 oxidation as it were, then we obtain this structure. All right. So now what I'm saying in essence is, so when you oxidize this, okay, so you obtain, this oxidosqualene. So then when you protonate this, that is usually in the presence of an acid, okay, then what you then obtain, okay, is this epoxy, derivative. So then this oxygen atom here, as you know, is unstable. So this bond migrates here so as to provide the lone pair of electrons that is needed. thereby generating a kind of, nucleophilic center right in here. Is that okay? So by so doing, this will induce, these bonds to move over here. So thereby forming a six-membered ring. Is that okay? So similarly, okay, the bond there, okay, yes. So this cannot but also migrate, you know, to this position. Is that okay? All right. Then, okay. So down migrates to that position. Then, equally, yes. So this migrates here. Then this migrates here. So also this one migrates to this place. So by so doing, actually, we have been able to generate, you know, um, a kind of, what is it called now? So we have been able to generate a four-membered ring, one, two, three, four, okay? So three of which actually are six-membered, then the fifth one actually, which is a five-membered ring. So then we have this, okay? So now, in that sense, now we've been able to generate, a kind of, what's it called, a nucleophilic center here by so doing. Is that okay? Let me put it so very well so I can see that so very well. So it looks like this. All right, good. So when that happens, okay, now because of the proximity of this, so good. Before then, what happened is that you understand what we call a kind of ring string. Okay, this five-member drink actually it's not a very comfortable. Let me just say, because of ring strain, it is unstable. Is that okay? So therefore, there's going to be a kind of what's it called now? A kind of a shift, migration of this bond to this place. Is that okay? Good. So when that happens, so the result we obtain is this. So we obtain this. Is that okay? So now from here, okay, so by the now when this bond migrates to this place, okay, and then we have that, right in here, okay, all right, good. So right in here, so this therefore generates a nucleophilic center, on this ring, so that is at this position. Is that okay? So when that happens, okay, then don't forget we have, you know, our bond right in here. So this one is here, okay? So we have, good. Very good. So when that happens, then the next thing is that this guy here, okay, because of the proximity, migrate over here. So we generate a kind of a five-membered ring. So noted, every other point, remains, as it is. So this is our hydroxy group here. And don't forget, all along, there have been two positions right in here. So which actually was not indicated. So then we move. So on getting here, the next thing is we generate a five-membered ring. Our nucleophilic center now, at this junction. Is that okay? So we have this. So don't forget, we have this here, we have this here, we have one here, then there's another bond here, right? So good. So now, of course, once again, this is because of ring strain, the when you talk about cyclo or cyclic compounds, you understand me? So the larger the ring, the more stable the compound is. All right. The larger the size of the ring, the more because of what reduction in ring strain. As we move from let's say three-membered ring to four-membered ring to five-membered ring, six-membered ring, and so on. So in order for this to be stable, okay, there has to be what a migration again. Is that okay? So such that that bond moves over there. So when that happens, then what we then have is this. We obtain thereby generating a kind of nucleophilic center, at this junction here. Is that all right? So note all of this. Good. So now, the next thing that happened is that you know very well that actually there is a proton residence right in this place, this hydrogen. So this hydrogen cannot but just move. Is that okay? Then it moves over right into this. So we call it kind of 1-2 shifts. Is that okay? That's what we call an hydride shift. All right. So when that one happens, then there's going to be another nucleophilic center, at this junction. Is that okay? So, but then there's another bond right in here. Okay. So then what then happens is that this guy, you know, moves over and go and replace this one. Is that okay? Then the next thing that happens is that there's a proton loss. Is that okay? Such that this bond moves in over here. Is that okay? So if that is the case, then what we then generate is this. Now, each of these steps actually have various kind of enzymes associated with them. So I will soon highlight them as we'll soon see now. So let's look at it. So in this sense now, we have this. So this is what we have. And then we have a bond here. We have a bond there. So this actually what we call, don't forget all along, I've not just been introducing this. So there are bonds here, like I said. So watch it. Good. So then we have this. So actually this is the beta amyrine. Is that okay? That actually we are generating. Is that okay? And that one is made possible by an enzyme we call beta, amyrine synthase. Is that okay? So that is the enzyme that is responsible for that. However, from this junction also, okay, we can generate an alpha amyrine, okay, via alpha amyrine synthase, alpha amyrine, you know, synthase. Is that okay? So that one is responsible. The only difference between these two is that what we are going to have will look like this. Just watch it. You know, just permit me to manage this space. So in this sense, so if that is the case, so for alpha marine, what we have is this. Is that okay? So you can say actually we don't have 2-2 or we don't have a kind of dimethyl in this place. So actually it's a 1-2 configuration as it were. So then we have this, you know. So that is how we generate you know, that's how we generate alpha amino synthase. So now, if you go on and on, okay, we can have, because actually this particular ion here, we call it oleonyl, cation. Is that okay? So which actually is an intermediate, like I mentioned. Is that okay? So we call this one barakinyl, cation. Is that okay? So that is the pathway to this. Is that okay? So we call this one the marina, cation. So now, if there's a kind of hydride shift coupled with a methyl shift, okay, actually from this damarine ion, then we are actually going towards a lanosterol. Is that okay? So what will just happen is that instead of this bond migrating, the only thing that will just happen is that the hydrogen, in this point, will migrate to this place. Is that okay? So if that happens, then the next, so it's a kind of 1-2 shift. So this guy also will migrate to this place. Is that okay? Thereby inducing this methyl group to migrate to this junction, and then this one, to this junction. What I'm saying in essence is that this one goes and replace this. This one migrates to replace this. Then there's a methyl shift. This one goes up. Then this one actually comes down in here. And then there's a proton here. So the only thing that happens is that there's there's an hydrogen here. So there's a proton, okay, loss. So when that happens, then what we just generate actually is a lanosterol. And that's how this one looks like. So, and that one is via what we call LS. That's lanosterol synthase. Is that okay? So that is the enzyme that is responsible for that, catalysis. So this is what we have. So one, two, you know, Okay. So 1, 2, 3, 4, 5. So we have that. So that's actually how a lanosterol will look like. So there's a double bond there. So every other thing remains, the same. So that is what we have. So that is if, so we call this lanosterol. Is that okay? Aha. So take note of that. So actually, in that sense, now we just call the kind of protosterol, you know, protosterol, cation. So if that is what is actually taking place right in here, so that is actually how we can go from 2,3, oxidosqualene, to beta amerine or alpha amerine, considering all the necessary, steps that are involved in this. So take note of that. Thank you so very much.